In this video, we're going to be proving our trig identities, and I'm going to be going pretty quick, so feel free to pause and look at these steps if you need. But this is really only if you're interested in where these identities come from. Now, I proved the Pythagorean identities in the lesson video, so I'm going to be extremely fast with those. So I'm bringing in the trig diagram. It's being really slow to bring it up, but there it is, okay? And then I think about the Pythagorean theorem, which is a squared plus b squared equals c squared. And I just got to be careful because c's got to be the hypotenuse, but if I, kind of work with that, I'm going to end up with cosine squared theta plus sine squared theta equals 1, which is kind of what I was trying to show in the first place. Okay, and then with the other trigonometry, or the other Pythagorean identities, I'm going to just start with sine squared theta plus cosine squared theta equals 1. And then first, I'm going to divide both sides of that equation by cosine squared theta. And that's going to give me the first one, that tangent squared theta plus 1 equals secant squared theta. And then I'm going to divide both sides by sine squared theta, and that'll give me the other one, that 1 plus cotangent squared theta equals... Wait, I wrote that wrong, definitely. Okay, well, hopefully on the thing you're looking at, it looks a little bit better than that. There we go. That's much better. Let's move on. All right, now let's talk about the even and odd identities. So the first one says cosine of negative theta equals cosine of theta. And so I'm just going to start by thinking about an angle theta, right? And drawing the terminal ray of that angle. And it's going to intersect the unit circle at some point. Now the x-coordinate of that point, that's going to give us the cosine of angle theta. So I'm just going to mark that off on the x-axis right there. And then I'm going to think about negative theta, going the exact same amount of rotation, but clockwise instead of counterclockwise from the positive x-axis. If I draw the terminal ray of that one, okay, and make note of the point at which it intersects the unit circle, and think about the x-coordinate there, I can see that the x-coordinates, they're lined up. It's going to give me the same thing. So I'm going to have the same cosine because I've got the same x-coordinate there. Now for the identity for sine, I'm going to kind of have the same idea. I'm going to start with an angle theta. I'm not going to give quite as much detail when I'm drawing that. And I'm going to track the sine of theta. Okay, well, the sine of theta is the vertical distance from the x-axis, or it's the y-coordinate. And so I'm going to look over there and kind of mark where I think that is on the y-axis. And then I'm going to think about negative theta. Okay, which should be, about down there. And if I kind of think about the sine of that angle, okay, the y-coordinate of that point, it's going to be down underneath. And you can see, I didn't even draw it all that well. You can see that it's about the negative of the upper point. And so that's why the sine of negative theta is the negative of sine theta. Now, I could go in and draw you the graphs of y equals cosine x and y equals sine x and point out the symmetries around, okay, for cosine, the symmetry around the y-axis, or for sine, the symmetry around the origin. And that is going to give us the fact that these are even and odd functions. But I think visually speaking, going back to the circle, this is a better representation of why these identities are true. All right, now for the sum and difference identities, these are going to be a little more intensive. So I'm going to start off with these two diagrams, and I'm going to start by showing you the difference formula for cosine, and then I'll be able to use this and the thing I just showed you to get the angle addition formula for cosine, and then we'll use a different diagram for sine. And then I'll give you two different flavors of what this proof might look like. So we're looking at the distance between points P and Q and the points P prime and Q prime. And if you look at it, they need to be the same, because this distance from P to Q in red is really just going to be the same. We've rotated it down by beta radians, basically. Okay, so rather than looking at alpha and beta separately, we're going to look at alpha minus beta against 0. So we're going to set those two distances equal to each other, and we're going to work on the distance formula. So remember, it's been a while since we've used the distance formula probably, but it's the difference in y's squared plus the difference in x's squared square rooted. So the square root of y2 minus y1 squared, so I'm working on PQ right now, the distance in red. So sine beta minus sine alpha for the y's, and then cosine beta minus cosine alpha for the x's, square those, add them together, take the square root. That's the distance PQ. And that's going to be equal to another distance, P prime, Q prime, but that'll be a little bit easier for us to work with because the coordinates of Q prime are 1 and 0. All right, so on the y's, I'm going to have 0 minus sine of alpha minus beta. And then on x's, I'm going to have 1 minus cosine of alpha minus beta. Okay. And then I'm going to kind of simplify these expressions and work around and do a bunch of algebra. So first, I'm only going to be working on the square root on the left. Okay, and I'm going to actually square those things out, and you see it's going to be a lot, yeah. I'm going to have the sine squared alpha plus sine squared beta when I FOIL the first expression, minus 2 sine alpha sine beta. And then when I FOIL out cosine of beta minus cosine of alpha times cosine of beta minus cosine alpha, I'm going to get cosine squared alpha plus cosine squared beta minus 2 cosine alpha cosine beta. Now I'm going to have room to deal with the other half of that equation. I think I just want to simplify this first, because what I'm going to do is I'm going to collect the sine squared alpha plus cosine squared alpha, and that's going to make a 1. And then I'll collect the sine squared beta and the cosine squared beta, and that will make another 1. So I'll have eventually the square root of 2 minus 2 sine alpha sine beta, and then negative 2 cosine alpha cosine beta. Okay, and that's still just the left side of that original equation. Now I'm going to work on the right side, okay, that second square root. And I'm going to say, all right, well, if I actually square those things out, 0 minus that thing squared, I'll just have sine squared of alpha minus beta. And where is that going to be? And then plus cosine squared when I FOIL out the 1 minus cosine of alpha minus beta, plus the 1 when I square the 1, and then minus 2 cosine of alpha minus beta. You can barely see it in there. I think this is my best shot at fitting it all into the screen with the diagram and everything. And now I'm going to square both sides. But while I'm squaring both sides, I'm going to, do a little bit of work on the right side of that new equation, because I've got a sine squared of alpha minus beta plus cosine squared of alpha minus beta, and that's got to equal 1, because sine squared theta plus cosine squared theta equals 1 for every theta. Now on the left, I've just, squared that square root. And then on the right, I think, I'm going to have 2 minus 2 cosine of alpha minus beta. And now I'm really close, actually, because I've got this cosine of alpha minus beta. Okay, and I'm going to solve for it. First, I'm going to subtract 2 from both sides, and then I'm going to divide both sides by negative 2. And then I'll have what I'm looking for. Cosine of alpha, cosine of beta, added to sine of alpha times sine of beta. And that's the difference formula for cosine A minus B. Now, if we wanted to show the addition formula for cosine, we're just going to use the subtraction formula that we just developed, and then we're going to kind of substitute on beta. So we're going to let alpha equal A and beta equal negative B. So we're going to set up kind of with the formula that we've got of a difference, except I'm going to substitute A in for alpha and negative B in for beta. And then we're going to do that on the right side of the equation, right? Everywhere I saw alpha, I'm replacing it with A, and everywhere I saw beta, I'm replacing it with negative B. And then I'm going to need to recall the even-odd identities, that cosine of negative b is equal to regular cosine of b, and sine of negative b is the negative of sine of b. And then when I apply those, I'll have what I'm looking for, right? I'll have cosine of a plus b equaling, okay, well that sine of negative b became negative sine of b, and I'll factor the negative out the front. And then cosine of negative b, that became regular cosine of b, and this is what I was, hoping to show you. Okay, now to show the angle addition formula for sine, I'm going to use a more geometric approach. I'm going to use these two triangles that are stacked on top of each other. And I just want kind of the hypotenuse of the triangle with angle B in it to be 1. Okay, now really what we're going for is the height of this red line. Okay, that's going to be the sine of A plus B. Okay, and just before we even start, I'm going to tell you I'm going to use A prime and B prime to represent the complement of A and B respectively, because we're going to need those as we move forward. Now, the first thing I would ask you to notice is on the upper triangle, that this leg is cosine B. And I do mean all the way from the angle that, or the point that angle A and B share all the way to that upper right angle. Okay, that's cosine of B, because cosine of B is equal to that leg divided by hypotenuse is 1. Okay. Then I can say that the outermost vertical leg on the lower triangle, the one that's not got any red on it, that's going to be cosine of B times sine of A, because of opposite over hypotenuse. That's what sine is. Okay, and so then from there, I'm going to say, okay, what am I going to notice next? I think I'm probably going to go in and, I don't know if you can see that little horizontal line that's drawn in gray. I'm going to think about the triangle that's underneath that. That's going to be really important for us. Okay, we're going to need to look at that, and I'm going to kind of give it some color, and I'm going to pull it off to the side and draw a larger replica to work on it a little bit, because I actually need to jump in there and look at the angle. Okay, now I'm proposing that by alternate interior angles, like the z thing from geometry, I'm going to need to use this in a really long time, the angle in that yellow triangle is also going to be A, okay, because the two parallel lines, the blue line and the horizontal line at the bottom are parallel. They're cut by that transversal that's the hypotenuse of the lower triangle, and so alternate interior angles will be equal. Okay, from there, I'm going to say, well, I think that's actually not what I noticed first, that that's going to be A, but the reason I need that to be A is that that angle that's kind of part of the right angle that's been cut off, that's going to be A prime, right? The yellow angle that I know is A plus A prime does add up to equal that right angle, that 90 degrees. Okay. Now, if I have a complement in the bottom right of the triangle that's not colored in yellow, okay, that means that the upper one that's just kind of like labeled as A, that's why that has to be A, because we do have a right triangle, or we have a right angle where the red and blue line segments are intersecting. Okay. Now, at this point, I think I probably need to label the outside. Yeah, that's going to be sine of B. And I might should have started there, but that side there is going to be side B. If you look at the big upper black right triangle, okay, that'll be sine of B. And then I can figure out the height of the red line that's above the blue segment by just doing more trig. You know, cosine of A is going to be adjacent over hypotenuse, and in this case, hypotenuse is sine B. So that adjacent side will be sine of B multiplied by cosine of A. And, you know, once I get that, I've pretty much got what I need, because I'm just going to add the two pieces of red together to get the value, the full length of the red line. So I'm going to say sine of A plus B, that's the length of the red line, is going to equal this first piece plus the second piece. And then if I actually just write it out, well, that's kind of what I'd set out to show in the first place. So that's the angle addition formula for sine. And if I wanted to show the subtraction formula, well, I'd just kind of substitute B in, or negative B in where I had B before, and so I'd just kind of set up my skeleton, and I'd plug in A and negative B, and so I'd just go in there and actually fill in those places, and I would recall that, you know, the even and odd identities, that cosine of negative B is regular cosine of B, and sine of negative B is the negative of sine B. And then kind of put it all together and get sine of A minus B is sine A cosine B minus sine B cosine A. Okay, the cosine of negative B, that negative just went away, and the sine of negative B became the negative sine of B. All right, now let's get those double angle identities. So sine of 2 theta is going to equal 2 times sine of theta times cosine of theta. And we're just going to use the angle addition formulas to generate these. So we know that the sine of A plus B is sine A cosine B plus sine B cosine A. And I'm just going to substitute theta equals A and theta equals B. So I've got the skeleton. I'm going to say, all right, theta plus theta, that'll give me 2 theta. And I'll just replace A and B both with thetas. Okay, and then I'll see, oh yeah, I'm going to have 2 of these sine theta times cosine thetas, so that'll give me sine of 2 theta equals 2 sine theta cosine theta, like I'd hope to show you. Double angle formula for cosine will be just as easy. We're going to start off with the angle addition formula. Okay, cosine of A plus B is cosine A cosine B minus sine A sine B, and then we're going to kind of plug in theta and theta for A and B. So that'll give us cosine of 2 theta. We're just going to plug in theta for B, okay, and then we're going to look and see, okay, this is giving us just what we want. We have 2 powers of cosine theta, that's cosine squared theta, minus sine squared theta, that's going to give me cosine of 2 theta. Now, the last thing I need to prove for you for this video is going to be kind of the corollary to the double angle formula for cosine. These other formulas that also work, that kind of only have one trig function, either only cosine or only sine. And so I'm going to start off with the double angle formula for cosine that I just proved, and then I'm going to, use one of the Pythagorean identities. I'm just going to, use the fact that cosine squared theta is 1 minus sine squared theta, and that's because cosine squared theta plus sine squared theta equals 1 for every theta, and I'm just going to make that substitution. Cosine of 2 theta equals 1 minus sine squared theta minus another sine squared theta, and that'll give me 1 minus 2 sine squared theta. And if I want to show the other one, the one on the right, cosine theta is 2 cosine squared theta minus 1, I need to get rid of the sine squared theta. So I'm going to use sine squared theta equals 1 minus cosine squared theta, make that substitution, and then, if I look at it, it's like, oh, minus the negative cosine squared theta, that's where I'll get the second cosine squared theta, and that was what I was hoping to show you. All right, so that's all the proofs for this video. Thanks for watching.